Hey, Data Skeptic listeners, I need one more week before I can kick off our next season, which, why don't I just go ahead and tell you right now? The new theme is going to be called Consensus. It's a great broad topic that I'm going to cover from a bunch of different angles. I'm really looking forward to sharing all that with you. We've been lining up the last, locking in our interviews for the whole season, so I need one more week or two to get that first episode out to you. In the meantime, in order to not leave everyone hanging, I'm going to share a few details about how fraud detection systems are built at scale in industry. My thoughts here are informed by conversations with colleagues, research papers, and my own professional working experience. I've done fraud detection in several different settings and with a technology suite that's evolved very quickly while I've been working. It's getting a lot easier to apply algorithms at scale to fight fraud, and as a result, fraud is getting more sophisticated, to be perfectly frank. Have you guys heard these reports about people getting mysterious seeds in the mail from China? This has all the makings of a really good Michael Crichton novel, am I right? What would you do if you got a seed in the mail? Probably throw it away, like, why did someone send me this? It goes to a landfill, and then it grows into this man-eating pod person thing. Or actually, no, sorry, better than that. It turns into some sort of agricultural bomb. People say World War III will be cyber warfare. Maybe it will be agro-warfare. An invasive blight and attack on agriculture? Scary stuff. Michael Crichton, give me a call if you need some help with this. But the truth about these seeds seems to be much more mundane. See, online, sales are driven heavily by algorithmic components of scoring. And while those algorithms are, generally considered to be proprietary, there's a lot of back channeling and reverse engineering that goes on. And one of the important metrics that many of these sites, I think Amazon in particular, uses is the number of and quality of reviews. So as you've learned from our episode on Goodhart's Law, Goodhart's Law states that when a measure becomes a target, it ceases to become a good measure. So a very well-intentioned person said, let's base our search algorithm on the number and quality of reviews. So what happened? People posted mass amounts of fake reviews. Or maybe I shouldn't say people, but merchants or vendors working for merchants. And if your competitor's doing it, well, by gosh, you better do it. And it's an arms race. So how did the platforms respond to this attack on their algorithms? Well, they said, we need these to be verified reviews, or let's weight them differently. So the unverified reviews weighted very low, perhaps even zero. Verified reviews, really important. People actually bought the product. That's great, right? So if you have an interest in creating a verified review when you are not a legitimate customer, and you're required to have some proof that you purchased something, well, you create a sock puppet, a fake person. Find a real person that you're going to imitate. Just a name out of a phone book somewhere, and literally mail them something. That way you will have a postal receipt proving that you shipped something. An actual transaction took place. Money was actually exchanged. The sock puppet had to pay Amazon. Amazon took their cut and gave the rest of the money to the merchant. And, lots of people with their finger in the pie. I'm sure a credit card company got something and all that. But this merchant bought something from themselves for, let's say, $10. They got $9 back after all the fees and whatnot. Not a great business model in and of itself in that regard, buying your own products. But in this case, the cost is pretty low. You shipped out a seed, something that costs very little, I suppose. And now you have the opportunity to post a more convincing fake review. The platform is likely or more likely to be fooled by this. Now, what a great use of Occam's razor, everybody. We went from agro-warfare down to cheating on the Amazon marketplace. Now, if you happen to get seeds mailed to you that you weren't expecting, coming from China or anywhere else, I guess, anybody could do this, even though China seems to be the place you hear about most on the news doing this, what you want to do is call the Department of Agriculture or follow up with them. Maybe their policy will change in the future, but that's what I heard you're supposed to do, just to double check this. Lots of false alarms here, but actually, if anybody gets one of these, I'd love to hear from you. Just curious, because I think this might be a rare phenomenon, but it is a phenomenon. It is a real-world behavioral change in order to produce more fraudulent results, to artificially boost one's own products in the marketplace. So fraud's a pretty big problem, right? Let's focus today just on e-commerce, because I think that's a general framework everyone can understand, and it highlights most of the typical problems that come up in fraud detection. So for this episode, I'm going to kind of do a survey of the techniques I'm aware of and talk about a few use cases. First and foremost, I really want to have a focus today on a discussion about software architecture. Well, you know me, I love methodology and research and algorithms. The truth of the matter is, if you want to be effective, you have to start from a very strong software foundation. And this is what a lot of organizations get wrong, actually. This is a very critical piece that I see many companies get completely wrong. Or maybe it's that the companies that get it right the first time don't end up ever talking to me because they don't need my help. But something I've had to help a lot of organizations with is kind of unwind a boondoggle system and put this together in the right way. So let's first define the problem here. Why don't you rewind back to about 1896 and following on the tail of the Guinness Brewing Company's strategic hire of William Seeley Gossett, the Sears Roebuck Corporation was desperate to find a great statistician to help sort out their mail order fraud problem. Is that true? I have no idea. I would love to research how mail order catalogs like that dealt with fraud and bring you an episode. If you'd like to see content like that, you guys got to sponsor us. Thanks to those of you that do. Head over to dataskeptic.com. Either get something out of our store or click on members login. Support the show so we can keep bringing you this content and expand our offering into fun stuff like that. In any event, let's talk about more traditional e-commerce. Now, listeners to Data Skeptic will know I'm inclined to tackle this problem with machine learning, and it seems like a pretty straightforward classification problem, right? You have many transactions, some are fraudulent, some are not fraudulent. Figure out a way to predict which is which for a new transaction. Now let's talk for a moment about labeled data sets. E-commerce is done almost exclusively on digital payments, mostly credit cards, but PayPal, Bitcoin, Apple Pay, that kind of stuff is also available a lot of places. In fact, credit cards are still the vast majority of the transactions, so let's focus there. In fact, credit cards are the reason fraud is really a problem. In something like Bitcoin, once the money is collected, there isn't any mechanism to get it back. Merchants could easily steal from consumers. And I feel personally thankful that we don't live in a world where that's the case. My credit card provides me some semblance of a middleman between myself and the merchant if a dispute arises. And with my credit card company acting as a middle agent, I can issue disputes. So if I didn't get the goods or services agreed to and I can't work that out with the merchant, I might contact my credit card company and say, hey, I'm disputing this charge, false advertising or whatever. I guess more commonly, or the case in terms of fraud, is call and say, I've never seen this charge before. Someone has done a fraudulent transaction. Please reverse that. Let's cancel the card and the whole shebang. So any sort of dispute like that, the industry jargon is to call it a chargeback, because the merchants receive the money. As soon as the credit card company smells anything foul, they immediately take that money back from the merchant. So some merchants that run on thin margins, that can be a real problem. They don't want to lose that, let that money get into limbo, I guess you could say. So sometimes these disputes need to be broken down by, is it fraud or is it this or that? And the data scientist has to ensure that they get the right label. But if you link that chargeback back to its original transaction, just join that some kind of way, you now have a labeled data set, right? Well, kinda, sorta, yes, but couple of things. First, there's a delay in that signal. If it's truly fraud, not everybody checks their card statement every day and that kind of stuff. There's always some period of time. In fact, it's rather generous to the consumer. You get quite a bit of time, sometimes like 60 days I've seen these come in. So the consumer says, oopsie, here's something I don't remember doing. I'm the victim of fraud. Reverse that transaction. So there's a lag between the actual event and the signal. Not the end of the world, but one needs to account for it. Maybe you need some fancy survival analysis. Probably you need something simpler. Speaking of survival, there's the survivor bias going on here. The only charges that get marked as fraudulent are those that went through and became fraud. If you're building a good system, that number should be very small, so you start to starve yourself of training data potentially. Broadly speaking, the solution to that problem is to model behaviors rather than particular flags. So if you wait a couple of weeks, all your chargebacks will have come in, and then voila, you have a wonderful labeled data set of the transactions that did charge back and those that didn't. This will be an imbalanced data set, so you definitely need to address that problem. In fact, just for fun, you and I right now are going to build a 99% accurate fraud detection system, okay? It's a rule-based system, and here's the rule. As a charge comes through, look at the charge, look at all of its properties, and no matter what they are, say it's not fraud. 99 times out of 100, you will be correct. You are 99% accurate, yet you are also completely useless. That class imbalance problem is tricky for machine learning. There are good ways to account for it, of course, but pay attention as you go through these problems to that sort of thing. Accuracy is really a misnomer in a problem like this. Look at F1 score or other things, but honestly, you need to be looking at your confusion matrix and understanding what your model's doing, since it's focused on such a niche group, or identifying this niche group that, to be frank, might prefer it not be identifiable. Fraudsters do not generally advertise the fact that they're fraudsters, although their metadata may give them away. Okay, so we've got a nice training data set, a labeled data set, which is exactly what we want. Now, this data set we've just talked about using historical transactions, it's generally pretty useful. That's a nice kind of free lunch that you get those labels eventually. And if you train a machine learning model using those labels, you will very likely get a model that is good at predicting the types of fraud you've seen previously. Now, that assumes that the features you give the model have enough information content to actually detect that fraud. There has to be a signal in there for the machine learning to find something. It's not magic. But assuming to some degree it's able to accurately predict whether or not a transaction will or won't become fraud, that system can generalize only within the types of fraud it's seen. And Goodhart's law will slap you in the face in this process, because the minute you start declining transactions to a fraudster, that fraudster has to make a decision. Do I give up or do I try something else? And in general, while you might get some people to give up, there's always someone who won't give up. The standard I've set with a lot of my clients is to say, you just need to be marginally better than your competitor, and people won't commit fraud with you, they will commit fraud next door. You can't stop this behavior, you just heavily disincentivize it and make it difficult. And you're going to need a system that's evolving. As you identify and prevent fraud, that will almost certainly force new forms of fraud to emerge, unless you just completely solve the problem forever and ever, right? A naive approach would say, okay, well, let's just set up a nightly or weekly batch process that gets the latest, let's say, rolling 90-day window of data, trains the model on that, even does some fancy, red-blue comparisons to the existing model, rolls it out. Nice idea, probably necessary, but definitely not sufficient. It's too slow. While we can hyper-focus that our fraud is rooted on a single transaction, fraud begins in a much bigger picture, and users that commit fraud often have much different behaviors and metadata. So now begins the really, really fun stuff, at least from my point of view, the clever things you need to do as a data scientist. For example, here's an easy one that everybody knows. Does the shipping address match the billing address? If not, doesn't mean it's fraud, right? I could ship to my office, or if I had a vacation home or something like that while sending my bills to a primary residence or P.O. box or whatever. But if shipping and billing are equal, certainly we can have a little bit more confidence that this is not a fraudulent transaction, or at least that's intuitive. Maybe we let machine learning decide whether or not it values that feature, or I should say to what degree it values that feature, how it uses it. But you'd be hard-pressed to argue that that's not a valuable feature to have. So take that a step further and ask a question like, has this customer purchased with us before and mailed to the same address? And the assumption is that they have no history of fraudulent transactions, that you would have already been blocking them if they were on strike 1, 2, or 3 here. But no, okay, this is a person who orders the same thing on the first of the month every month for the last 12 months, and on the 13th month, the next order comes in. I guess that could be fraudulent, but we have a lot of evidence to the contrary in the simple time series I described. Now, here's an important thing. If you learn one thing from this episode, it's this. Those features I just described, well, does shipping address equal billing? That does exist in your transactional data. But how many successful previous orders has this person had? That does not. What do I mean by transactional data? Well, if you start an e-commerce company, the first technological hurdles you have to jump are getting your site up, allowing people to use a credit card to make a purchase, to put it in the cart, complete all that order, track it, fulfill it, mark it complete, operational transactional things. You probably have a database somewhere with tables that have names like customers, orders, order details, shipping. And that's great. That is the full grain data that describes all of the transactions. All the information is there, but not really in a form that's useful to this algorithm. Now, a mistake, and actually I don't see people making this mistake very often anymore, but if we think, hey, we need to know the previous number of successful transactions, people might alter the transactional schema and start to stick that data in there so that it can be aggregated up. For reasons I don't want to get into here, that is completely wrong. If anybody needs to know more about why, send me an email. I'll help you out. Leave the transactional data alone, but find a procedure to aggregate and transform it into more useful data for your machine learning process. All right, now let's get into the interactive portion of the show. I'm going to do a little brainstorming about other features like that, like the shipping equal billing. Why don't you pause and come up with your own list? Either if you brainstorm it or write something down. Then compare your list to mine. I would love to hear if anybody comes up with clever things I didn't think of. Send me an email, kyle@dataskeptic.com. And here is what 6 years of podcasting teaches you. Please, everybody, in the subject line, put fraud detection feature engineering ideas. especially if you're listening to this and it's no longer August of 2020 as this will be released. If it's, I don't know, July of 2024, realize I might not have context for what happened 4 years ago. Give me a quick refresher about what you're doing. Still would love to hear from you. I get back to everybody, although quite slowly lately. I'm going to ask you generic questions that might lead you towards some good features. First question, is this order from a customer that is a real person or company, or is it a valid client, I guess? Second question, do you believe that that real person is actually the one that placed this order? Third question, will that real person pull any shenanigans later? That's a high-level decision tree, but one that I think pretty well encompasses all of the details you might want to break into. All right, pause now if you want to play the game, because I'm going to start brainstorming my features. All right, first one, let's knock out an easy one. The number of prior purchases. And as an aside, for people new to machine learning, this is one of the first things you learn. You go in and you build some classification problem and you look at feature importance, right? What is driving my model? And by and large, the most prominent feature should be something obvious and boring. Where is most of your fraud going to come from? People with 0 prior purchases, obviously. But that's also where you start a future long-term customer. So you got to be careful not to filter out too many people or filter on that alone, of course. After a number of prior purchases is in place, I would move on to what I call IP address metadata. There are a number of services where you can either buy a batch download or use a real-time API, which is what I'd recommend you do. Let me run my own record right now. So I use one of these services at Data Skeptic. The metadata I get back, city, country, host name, which my host name, I'm not going to read all of it off, but it's something.sbcglobal.net, and it tells me a little bit. That's my internet provider. Although for some reason the org is listed as AT&T Services Inc. with some sort of code in front of that. I get an approximate location, lat long, time zone, region, postal code. All of it's accurate. The postal code is off by 1 digit, but that's fine. So what am I expecting here? Are AT&T customers more likely to commit fraud than some other company? Not really. But you don't always see residential IP addresses here. If that IP address is owned by, let's say, Amazon Web Services, that's a little suspicious, right? Why is there an EC2 instance or Lambda function or whatever making a purchase on your e-commerce store? Probably because it's a bot. And look, I don't discriminate. We have a store at dataskeptic.com where you can buy t-shirts and stuff. We take money from humans. We take money from robots, primates. If you have a credit card, I accept it. However, I do acknowledge that while I haven't yet had, to the best of my knowledge, any automated or bot-driven purchases, those are very likely to go fraudulent. So there's a powerful and, again, sort of obvious feature. So this IP address metadata is not readily useful to me right now. Maybe I have to get some big taxonomy of, is this a residential service or otherwise? Maybe even some of these services will give you that flag for free. Perhaps I'm in the cheap person tier with what I subscribe to. I'm not sure. But it's no stretch of the imagination to think you can label some interesting categories like this is residential versus commercial. And maybe you even want to try linking that to the shipping billing. We should do the same thing with browser data. And actually, browser data is surprisingly useful because people are surprisingly sloppy. Similar to IP address metadata, your browser emits a wealth of metadata. A user agent string contains a bunch of information about your browser and your machine, not necessarily enough to uniquely identify you, although sometimes that can happen. But there's a lot of stuff that your browser sends to web servers. Or for people who write bots, there are often many blank fields that should otherwise be populated. If the user agent string is empty, that's suspicious. That's either someone doing something nefarious, probably 9 times out of 10, or 1 out of 10, it's a technically savvy person who is privacy conscious and is, has overridden their browser settings or something like that. Of a very good customer, potentially. You don't want to just block them on that alone. But by and large, missing browser metadata is a red flag. Another great example is catching lazy fraudsters. So look in that browser metadata. Sometimes you can tell things about the machine, like what operating system it's using, what version of the browser, and most importantly, the language settings. As I recall, I worked with a front-end guy, and it's language settings for your keyboard that we were able to extract. I don't know the front-end aspects of the work that person did so well, but they were able to deliver me a flag called is_Cyrillic. And like all good features in fraud, that's not an indictment. Having a Cyrillic keyboard does not make you a fraudster. Nor does living in Montana and having a Cyrillic keyboard make you a fraudster. That's perfectly fine. Rare, but fine. But having a Cyrillic keyboard and a Russian IP address and a Montana billing address, but a Canadian shipping address, that's all a bit too much for me. You can get metadata from the payment, what type of card they used. And I think there's a bit more that credit card companies can back channel with you, and you can learn things about how long that person's been a customer. I'm not 100% on that because I've never found those sorts of features to be very useful to me, so I haven't pursued that, but I think that's out there. But now let's get into my favorite feature, or really it's a meta feature. Counting frequencies. So let's go back to our friend in Montana with the Cyrillic keyboard. That's a rare individual, but could be a real individual. So let's count, How often do we see the frequency of Montana? How often do we see the frequency of that keyboard? And how often together? So frequency alone. Your e-commerce store probably gets regular orders from the state of Montana. Depending on your volume, it's daily. Maybe you're a big company and it's 100 orders daily to that state, which probably means there's, 10x that in other states. The population of Montana is a little bit small. And you probably have cyclic things like weekly and monthly cycles. So you want to normalize that all out. Why don't you just calculate for today or last 24 hours, whatever is convenient to calculate, what is the percentage of orders you've been shipping to Montana or coming in that should be shipped to Montana versus your typical daily percentage? And if it's not so far off, that's standard. But if you go from 1% of orders to Montana to in a single day 20% orders to Montana, something's suspicious. Not to be a broken record, but again, not necessarily fraud, but definitely go look into that. Something's peculiar. So going back to our IP metadata, we should expect that, if 20% of your orders come in from AT&T home internet lines, that's not the kind of thing that should just randomly change overnight. You expect consistency, and when you see deviation from that, that's an indicator that something might be up. Something is weird. So why don't we turn those frequencies into features and let the machine learning algorithm that's coming decide whether or not something's suspicious. So now we've enriched that transactional data. What previously was not helpful for machine learning is now transformed into features that are helpful. There are things you can do with cart analysis. Look for common purchasing patterns. Maybe something like Jacquard similarity could be helpful to you here if you have a lot of items per purchase, like a grocery store kind of situation. I'm told that this is actually a really good signal in brick and mortar businesses, that there are certain hot ticket items people tend to steal, and eventually those are the kind of things that get put behind counters or behind locked doors and things like that. And anecdotally, I'm aware that for whatever reason, people who steal and skim cards often use gas stations as like their probing point to test things out before going on to bigger purchases. So if you're a credit card company, that's a kind of pattern you can look for. At an e-commerce store, you don't know if previously that card was used at a gas station, which common behavior, but one that's maybe more frequent with fraud. But I guess maybe the equivalent in digitally is people who purchase things that are hard to get back, things that ship quickly or drop ship via another vendor, or they're a digital download or something along those lines. You as the e-commerce merchant, you actually have a nice little window of time between when the order comes in and when you ship it out. You want to be prompt with that, but you can take a minute and say, hey, does everything smell right here? Do we think this is an order that is legitimate we should send out? But broadly speaking, coming up with similarity metrics between known previous fraud and known previously good transactions can be an interesting feature or suite of features to use. Go back to that credit card situation. Let me talk to you a little bit about opportunity. As I said, an e-commerce company doesn't have any visibility into where did this person use their credit card previously, nor should they. It's none of your business. If you want to come to the Data Skeptic store and buy one of our awesome t-shirts, I'd appreciate it. But if previous to that you bought, gasoline, groceries, tobacco, or adult toys, it doesn't matter to me and it's none of my business. It's definitely none of my business. Doesn't matter to me. A little bit, actually. If the credit card company were willing to collaborate in some way with us and say, look, I know this guy ordered a t-shirt, but we're a little suspicious of him. You do what you want, but we're going to give you back some signal that this is an account that is on a watch list right now or something like that. We haven't blocked it yet, but use at your own risk. I suppose that exact example would never happen because it sort of opens up the possibility of some sort of culpability with the credit card or whatever. The credit card company really wants to put the risk on the merchant. But my last big feature is federated learning. So take an example of Gmail, right? Before Gmail and before Hotmail and all those other services, you'd set up your own POP3 web server or you'd sign up for one of these, and there were a cottage industry of free email clients. I guess there still are, even though there's, some big players in the space. But that's the point. The big players have the biggest set of examples. So if you get a spam email and you mark it as spam, that's a very weak signal. That's one person, could have been a mistake, could be fraud, someone trying to mark their competitors' emails as spam or something. But Gmail sees across all of those inboxes. And if there's a spike in frequency of some subject line or something like that, that's an excellent indicator that maybe it's spam. Gmail can federate the data of all its users. And in the same way, there's definitely an opportunity for e-commerce customers to federate their data. Now, this has to be done carefully, probably with considerations of anonymity, certainly with an eye to privacy and legality. But even if you're not interested in joining or organizing some sort of consortium of some kind in your industry, maybe you work at like a big box retailer that owns other stores. Like a lot of clothing brands are all owned by sort of these Frankenstein master corporations. Those teams should federate their data. If you commit fraud on one system, what's to stop you from trying to commit fraud with the other? So I said I wanted to talk mostly about software architecture, and I do, even though I had some fun brainstorming there. Let's get into implementations of these. In particular, some of the biggest mistakes I see companies make. First mistake, they immediately treat this like an offline batch problem. So picture this. Growing company, young company, has gotten very successful at selling this great good or service that they have, has built up a strong engineering team who is hyper-focused on making that transactional experience really good and well-tracked. In comes the first data scientist, who certainly does not have enough resources to make an impact. They're going to be burdened with both transforming that data, coming up with a model, getting a release process in place. It takes a team. And oftentimes that emerging team focuses on, let's just get one big, CSV, Parquet file, whatever together, train a model, and move from there. And yes, you will learn a lot treating it like a batch problem, but you're also going to bump into some issues. Fraud detection mostly needs to happen in real time. That's not completely true because you might let a transaction go through, and then if there's for some reason something you need time to verify, for example, maybe you have features that look at clickstream behavior of users on a website. So someone joined the site, paid a subscription, and only after that do you notice that their behavior is indicative of fraud or something like that. You can go back and reverse that transaction. And actually, that's a very popular process when you get into the operational ways these things get deployed. But for simplicity in this conversation, let's talk about fraud detection as that moment-in-time API. Your model has to be deployed somewhere behind a REST service. So as the storefront is about to submit the transaction, it says, oh, by the way, let's do one last check. Should we approve this person, yes or no? All right, in order for that model to make that decision, you have to pass it in all the features appropriate for that user. So for example, the feature number of previous purchases, that is not readily available. What you definitely do not want to do is have your store in real time submit some big group by SQL query that literally does a table scan of all your transactions, or maybe you've indexed the customer or whatever, but has to sum it up. That's going to be too slow. You need those sums pre-calculated, so you need some sort of mechanism either offline or tied into your transactional process that is keeping these features warm and ready. This system runs in real time. So take, for instance, those frequencies I was describing. How many orders to Montana today versus yesterday, the percentage of orders going to Montana. If you treat this as a batch problem and try and solve that offline, however you solved it is definitely not going to work in real time. So not only will the teams end up implementing it twice, wasteful and error-prone, but in all likelihood, the implementations will differ in some minor way. Latency often becomes a problem here. When it's offline, you can just sum over something to the millisecond. In a properly built event-driven system, there may be some lag that has to be accounted for. This is why my recommendation is always that those features become part of your real-time event streaming process, and that new features not be introduced in this old school way where you ask a data science team to take a sprint and go do research, but instead to empower that team to release the feature immediately, have a platform or system that allows them to deploy these details so that a new idea starts being computed or tracked immediately. Come in tomorrow and you'll have a new training data set to look at. Better yet, that training data set is the exact production instances you would have seen in the model, not some goofy offline batch process that you had to invest a lot of time in coming up with. I have observed this as a major ceiling and stumbling point for a number of companies, primarily in e-commerce, And this is because you generally have a very strong engineering team who did an excellent job deploying this transactional e-commerce system. In all likelihood, they don't have expertise in data science or BI and these sorts of things. Now, I have a strong personal bias for serverless computing and event-driven systems, especially in this sort of domain. So in my personal opinion, that is not only the right software architecture you should look at, but is especially convenient for all players involved to make these sort of processes happen. That outstanding engineering team that built the store can just emit events. They're probably already doing it, in fact, and they're probably really good at it. Maybe you need a BI layer that figures out how to aggregate that event stream, or just a technology that does it for you, and then a professional to help build a model based on that data set. I've seen some organizations at this point debate whether or not a feature was worth it to implement based on the complexity of implementation. In my experience, 9 times out of 10, it's kind of alarming when I find an organization having that conversation because it's typically the wrong conversation. Now, if it turns out that those features have some computational complexity, like polynomial time to compute, and that can't be done offline, then of course you can't use it. Good example of this would be graph features, if you want to know something about the shortest distance between 2 customers or something. In all likelihood, that's going to have to be computed in some offline or auxiliary fashion, because that's a non-trivial computation. And that's fine, that's reasonable, but these discussions of, is it worth it to implement this feature, in my experience, rarely focus on something like that matters, and it's more about whether or not the engineers think it'll be easy for them to build something. Well, while certainly the level of effort to engineer is a critical point to be informed, it is never the engineer's decision about whether or not it should be implemented. It is for engineers and data scientists to communicate this up to management to make a decision. If engineering says, hey, the level of effort is going to be too high for us to help with this feature the data scientists want, and the data scientists say, no, it's incredibly valuable, that has to bubble up. That has to be solved hierarchically. And again, 9 times out of 10, that probably indicates a fundamental architecture problem in the system. Why is it so hard to implement that feature? Maybe take a step back and reevaluate what you're doing and how you're doing it. It is common for companies to rebuild this sort of pipeline 2 or 3 times. And while that's often regarded as a failure, the truth is, you learn a lot by building systems, and systems are always built and rebuilt. You think Google search runs the same way today it does as when they launched it? Obviously not. Is there even a single line of code that's the same? I doubt it. Maybe. If fraud is truly your problem, you need a platform that enables your data scientists to be successful chasing it rapidly, without iteration cycles and heavy cross-departmental dependencies. So when you figure out what works for you, and let's say it's those frequency analysis things I was talking about, the percentage of orders today versus yesterday, make sure you have an elegant framework by which you can deploy ideas like that, not just a single feature. Remember, fraud evolves. As you make improvements, so will your adversaries. Your adversaries do not care about your release cycle or the QA process. The longer you wait to release a new feature, the better it is for them. Wow, that makes it sound like fraud is rampant. So let's conclude with a quick discussion about operational processes. If a data scientist comes to the table, is empowered by the organization, and does a good job, they will produce a model that classifies very well on new transactions this is fraud or it's not fraud. And they will also deliver the infrastructure that is scalable, reproducible, audible, all those good things, so it can be evolved and iterated on quickly. Success, right? Let's pop champagne, let's shoot off some fireworks, we're done. No, we're really not. That signal, this appears to be fraud or not fraud, is just one lap in the relay race. Now, it happens to be the lap where the data scientist pretty much gets to take a break next, but be aware of who you are passing the torch to. Very rarely does any company just immediately say, okay, let's use that flag. If it's fraud, deny the transaction. If it's not fraud, let it through. If it's not fraud, let it through. That's easy. Of course, do that. What happens when the system says this is fraud or it's above some probabilistic fraud threshold? Not up to the data scientist. Here's why. Companies have agreements with credit cards. Those agreements are often highly negotiated and have a lot of dependencies. For example, the credit card company doesn't want to have a lot of those chargebacks. For obvious reasons we don't need to get into here, right? So if a merchant has a large percentage of chargebacks compared to their competitors, the credit card company is probably better off just ending that contract, not doing business with them. Too risky. I believe this is an issue in the emerging cannabis industry where even banks, much less credit cards, don't want to work with some of these businesses because of how risky and quasi-legal some of it is. I'm a little bit more familiar with one particular industry. I don't want to name it, so I'll speak vaguely. You can imagine it's something like off-track betting or an adult website or like a gun ownership thing. I worked with a customer in that space, and well, listeners are welcome to morally object to all those products. I personally don't, but I respect your right to, be opposed to something like a off-track betting. But it is a legal industry, one that, again, does not personally offend Kyle Polich. Again, I'm speaking in hypotheticals here. I've never actually worked in off-track betting. Whether or not it's legitimate, there's sort of a stigma to the industry, perhaps, that it's quasi-legitimate. And the credit card companies will take that to their advantage. They will negotiate harsher terms on those people. They will say, so those companies are highly incentivized to be very protective of the charges they let through. In fact, I'm not going to give a number because I think that might be a little proprietary, but there is a single-digit number that often gets negotiated with, where the credit card company says your chargebacks have to be below that percentage, or else there will be consequences for you as a business. The type of consequences that it's not even worth trying to fight. So that is your hard decision boundary. Finance has to maintain vigilance here. And your is_fraud label needs to be in service to their efforts. So in this one use case I'm thinking of, again, I don't mean to insinuate anything about off-track betting. I'm using it as an anonymous placeholder. The company I worked with was super above board. Maybe there's fraud and corruption in that industry, I don't know. But at least the guys I was working with went above and beyond to do good at what they were trying to do. In fact, in cases where there were obviously fraudulent things happening to them. Someone came in, placed a bunch of bets. When their spouse saw it on the credit card statement, they freaked out and said, "Oh, I wasn't there," even though we knew they were. We had them on camera in the building. But the finance team decided to let the charge get reversed and credit that person. Oh, because that's another trick. If you just credit them, it's not a chargeback anymore. It's a credit, like a return. So your rate stays low. So there's a lot of these games that people have to play. As a data scientist, you need to be in service to those games. The is_fraud label is an important milestone, but just one tentpole. All right, so the TLDR on all this. Fraud detection really requires a smart, real-time kind of architecture. Your traditional, give me a big CSV file and I'll make you a model approach, doesn't seem to really work on this problem. You need something that has little or no iteration cycle and is adaptive to the changing behaviors and based on every bit of information you can squeeze out of what you have. Beyond the transactional data, there's clickstream data, there's partners, data appends. There's a lot of snake oil out there too, so focus on feature importance and what's going to service your org. And like I said, I would love to hear people's feature lists. If yours differed from mine, maybe I'll send some prizes out to the people with the most clever responses. Hit me up, Kyle@dataskeptic.com, subject line, whatever I said earlier, and or feature engineering for fraud detection brainstorming. Similarly, if you like this format, let me know. I could do more of these. They're rather easy to produce, but I prefer the interviews myself. But thanks for those of you who listened to the end. I hope this was helpful to some people. Join us next time for the kickoff of the new season. I'm very excited to present to you Consensus. We'll talk about voting and databases and all that good stuff. Until then, take care, everybody.